Welcome to Study Loop.
All right, let's look at Chapter 11, Problem 105. We have the following image, which is an electrostatic potential map for ethylene oxide, and they gave us the molecule written out, and it's a polar molecule. Use the electrostatic potential map to predict the geometry for how one ethylene oxide molecule interacts with another. And they want us to draw the structural formulas. And using the three-dimensional bond notation introduced in Chapter 5, show the geometry. So we're going to have to show the geometry of the interaction. So unpacking this, we're going to have two steps. We're going to have that first step where we're going to draw the structural formula. So we're going to draw it out like we did in Lewis dot structure back in Chapter 5. And we're going to use Vesper theory, meaning we're going to have to identify the central atom, count the valence electrons, and then connect all the bonds. And then down here, show the geometry interaction. So we're going to show the interaction between two different ethylene oxide molecules. So let's start with number one. We're going to draw a structural formula. So up here we have carbon, and it's attached to two hydrogens. So we're going to put one above and one below. So that's our central atom. Now it says that there's two of these. So we're just going to scoot on over, put another carbon out there. And this is what we did in Chapter 5. Nothing fancy, except what we learned before with Lewis dot structure. And we have one oxygen, so we'll put it in there. So we drew our central atom and we attached it. Now, step 2 was that we looked and counted all of our valence electrons. So we have carbon and we have two carbons. So those two carbons each, when we go to the periodic table, we found that they had 4 valence electrons they can donate to this molecule. So that's 8 total. And we have 1, 2, 3, 4 hydrogens. And we'll notice that hydrogen's in our first row, which means each hydrogen can contribute 1 valence electron. And when we go and look at oxygen, we will find it has 6 valence electrons that it can contribute to the structure. So adding all of those together, we'll find that we have 6 plus 4 plus 8. That's going to be 18 valence electrons. And looking at the structure, we're going to try to fill out all of our electrons, use them up to make this a stable molecule. So we're filling in oxygen. So it has 1, 2, 3, 4, 5, 6, and then this bond is 2, 8. So this oxygen feels 8, it meets its octet. That's perfect. It's a happy oxygen. Let's look at this carbon. It has 1, 2, 3, 4 bonds. Each bond gives it 2 electrons, so we know that it's happy as well. Each one of these hydrogens feels 1 bond with 2 electrons, so each one of these are happy. Now let's look at this last carbon here. Oh, this carbon has 1, 2, 3. So this guy is less than happy. He doesn't have enough electrons. We could probably put 2 here, but let's find out if we've used all 18. So we have 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17, 18. We've already used all 18, and we weren't able to fulfill all of our octets. So we know that this is not the correct structure. And that's what we learned in Chapter 5, was how to do Lewis dot structures. So let's look at this one here. This actually shows us the structure on the electrostatic potential map. It'll have an oxygen up top, bonded to a carbon, and it's in a triangle configuration. So we're just going to draw this out and look at how they interact. We're still going to follow the same rules with Vesper. Those haven't changed at all. So we know we have 18 electrons, and we've used 2, 4, 6, 8, 10, 12, 14. So we have 4 left. 3, 4. So oxygen has 2, 4, 6, 8 electrons, so he's happy. Carbon has 4 bonds. He meets his octet, both of them do. And then the hydrogens all feel 2 electrons. So this is our correct molecule right here. So we just drew out our structural formula and we have it correct. We've checked it. So now we're looking at a polar molecule. Do you remember what polar meant? All of our polar molecules have uneven sharing of electrons. So for us, that means that our electrons are not going to be shared evenly. And we're going to see that here. You see these electrons up here? We have an uneven sharing. So this is a slightly negative. And down here, there's no electrons, so that's going to be a slightly positive part of the molecule. That's perfect. So we've drawn our structure and we know that it's polar because we have our charge distribution up here with a ton of electrons and none down here. So now let's dig into this electrostatic potential map. The best way to represent data is often to map it. And electrostatic maps may look a little intimidating at first, but they're not very complicated. They're really boiled down just a relative distribution of electrons. So our red areas are going to be our negative distribution of electrons. So our negative area, where we have the most electrons. And this green area, or blue, is going to be the absence of electrons. And that's perfect. That is exactly what we have here. So we've drawn it out perfectly. We've shown that this area up here has a slightly a negative charge, and this bottom has a slightly positive charge. And what we know about positive and negative charges is there's a slight electrostatic attraction between a negative and positive charge. And showing these two molecules together, we are showing the geometry of that interaction, is that there's an electrostatic charge holding these together. And that's what we'll end up seeing in water as well. Excellent, we've just solved our problem. Why don't you go